Hello, Chem 213 students, and welcome back for this week's lecture videos. We're going to be covering the first half of Chapter 20, which is having to do with carboxylic acids and derivatives, and we will cover the second half of this chapter next week and also prepare for the second exam. So let's get started talking about carboxylic acids, beginning with their structures and their nomenclature as usual. So here we can see a number of carboxylic acids and their common names. So common names are very common for a variety of carboxylic acids. They're very regularly used, unfortunately, and so you may have to interchange between them. For example, what would otherwise be known as ethanoic acid is called acetic acid. Here you can say butanoic acid. Acetic acid is vinegar, and butanoic acid is responsible for rancid odors. And what you're going to see is that short-chain carboxylic acids here tend to have poor smells that people don't like. Hexanoic acid here is responsible for the odor of dirty socks. So again, things like sweat, these are due to the oxidation of oils that contain double bonds in them. They tend to make short chain carboxylic acids like this, which all, as you can tell, seem to have a strong smell. With acetic acid, it only smells really bad if it's concentrated, but these ones as well, but they don't smell so good. Lactic acid here is a 2-hydroxypropanoic acid, as it would otherwise be called. And we'll talk about the naming in a moment. This is responsible for the sour taste of sour milk. Acetylsalicylic acid here, which is again a common name here. This is the even more common name here is aspirin. 4-amino, the amino group here, 4-amino salicylic acid is used in the treatment of tuberculosis, and isoretinoin is used in the treatment of acne here, these being common names for these drugs. In terms of carboxylic acids, one that is very common is acetic acid. Acetic acid, the U.S. produces over 2.5 million tons of acetic acid per year, also known as vinegar, but it's often used in chemical reactions. So if we react methanol here with carbon monoxide and catalytic conditions here with a metal catalyst, rhenium, we'll get acetic acid, which can then undergo further reactions to produce vinyl acetate, which is used very extensively to produce other compounds like those used in paints and adhesives. Carboxylic acid derivatives, this is what's referred to as a carboxylic acid derivative. It's something that you can get by adding a group where the carboxylic acid is and changing what it is. And we're going to see that there's a number of carboxylic acid derivatives that can be produced and are very common in synthetic chemistry because they're used to go on and produce other organic chemicals. In terms of the naming, if you have a carboxylic acid, one thing about a carboxylic acid is that it's always going to be situated on a carbon at the end of a chain because it ends a chain in such a way that you have a carbon double bonded to oxygen, which is also bonded to oxygen, which is bonded to another hydrogen. In terms of the naming, the carboxylic acid is going to be our highest priority group now, higher than the aldehydes and the ketones, higher than the alcohols. It is the highest priority group. So if you have, for example, an alcohol group here, this is going to be secondary to the carboxylic acid group. So the parent chain will include the carboxylic acid group. So here, in terms of the naming, when you have a carboxylic acid, the name is going to end with oic acid. And the prefix is going to depend on how many carbons we have. This would be carbon number 1, number 2, number 3, and number 4. Since we have 4 carbons, our prefix is but, and we have only single bonds, so we follow up with and we say butan, and then end with oic acid because of the carboxylic acid group. Now again, carboxylic acid is the number 1 priority group, and so we're going to be giving it carbon number 1. It has to be a part of the parent chain, so here our parent chain would have 1, 2, 3, for 5 carbons, that would be just as long as going these other ways. So here we'll make the 5th carbon, this one on the left here with bearing the hydroxy group, and we'll have 2 methyl groups here. So we're going to have dimethyl. And so now we end the name here with the parent chain. So the parent chain is this one right here. It has 5 carbons, and it's all single bonds otherwise between the carbons. So we're going to call this pent for 5 carbons, pentan for only single bonds between the carbons, and they're going to end with oic acid. So the parent chain is going to be named pentanoic acid. Then we're going to name the groups. We've got 2 methyl groups. We've also got a alcohol group here, which we would end with anol if it were the highest priority group, but it is not. It is the second highest priority next to the pentanoic acid, so we're going to call it a hydroxyl group or hydroxy group. And so now we're going to end the name here with our parent name, so we say pentanoic acid. Then the H is going to come before M in the alphabet. So we're going to write the methyl group second. Both methyls are on the 4th carbon, so we write 4-4-4-dimethyl for 2 of the same groups. We say dimethyl because they're 2 methyl groups. And then we're going to say 5-hydroxy because on the 5th carbon we have the hydroxy group. Remember, in nomenclature, numbers are always separated from letters by dashes. And when you have 2 of the same group, you write a locant number for each of those and separate them with a comma. Since both methyls are on the 4th carbon here, we say 4-4 dimethyl. Again, the carboxylic acid must contain the parent chain. And so in this case, we would sometimes call this methanoic acid with a cyclohexyl group. It has a kind of special name here also called cyclohexane carboxylic acid, meaning a cyclohexane group right here, attached to the carboxylic acid group right here. And again, there are a number of common names that are very well entrenched in the nomenclature of carboxylic acids, including what would otherwise be known as methanoic acid, which would be the systematic way of naming it, is often referred to as formic acid, and you're going to see this on bottles and stuff. It's just extremely common, unfortunately. Acetic acid would be called ethanoic acid by the systematic name, but it's very commonly called acetic acid. Propanoic acid, propanoic acid, is often called propionic acid. Butanoic acid is often called butyric acid. Butanoic acid, again, 4 carbons here. And then benzoic acid is a common name that you must use. So for the other ones, I'd accept either one, but the systematic name is technically the ones I wrote below. The common names are the ones that are often actually commonly used. And benzoic acid is used all the time, so that's definitely one that you have to commit to memory, benzoic acid, which is when you have the carboxylic acid directly attached to a benzene ring. And we learned that in the chapter 17 about the aromatic rings. There are also very commonly in nature dicarboxylic acids, which have names that end with dioic acid. And so to name these, what you will do is you are going to say dioic acid here, and you're going to have a prefix that is the entire compound here. So this contains 5 carbons right here. 1, 2, 3, 4, 5. Okay. And so this would be pentane without the carboxylic acids, right? And we write the full name like the chain. So we don't say pentan dioic acid. We actually say pentane dioic acid. So that E is kept here when we name a diacid. And so that's the way they're named. If we had this, for example, This would be called, well, it's got 3 carbons, 1, 2, 3. So we call it propane for 3 carbons dioic acid. Now that said, that it's right here. This would be technically called, again, propane dioic acid, but it is very commonly called malonic acid, like all of the time. This would be ethane dioic acid, but almost everyone calls it oxalic acid. This, as you can see, would be butane dioic acid, having 4 carbons, 1, 2, 3, 4. But it is very regularly called succinic acid. And this is, again, pentane dioic acid, which is very commonly called glutaric acid. And these are very commonly metabolic intermediates. They're important parts of biochemistry. So when we start to talk about, for example, metabolism, carbohydrate metabolism, and other metabolic processes later on in the class, later in the semester, we're going to be coming back to these dioic acid compounds. Now, when we look at the carbon here, this carbon is going to be sp2 hybridized, the carbon in the carboxylic acid. It has 3 bonded atoms, x equals 3, no lone pairs, e equals 0. So its steric number, assuming there's no resonance going on, is going to be 3. And so it's going to be sp2 hybridized with 1 unhybridized p orbital involved in this pi bonding. And it's going to be trigonal planar. So it's got trigonal planar geometry. In terms of physical properties, the carboxylic acids have very extreme hydrogen bonding. They essentially make a double hydrogen bond here. So in each of these carboxylic acids, we have here an oxygen-hydrogen bond, very polar. It'll be partially negative over by this oxygen, partially positive over by this hydrogen. Likewise, we have a very polar carbon-oxygen bond here. This oxygen will be partially negative over here. And so a similar thing here, we have the partially positive charge of this hydrogen and the partially negative charge of this oxygen on the neighboring carboxylic acid. And that results in a two very strong together hydrogen bonds. And as a result, boiling points in carboxylic acids tend to be quite high, even higher than those in alcohols that we had previously discussed as having high boiling points due to the presence of the hydrogen bonding. Recall that carboxylic acids behave as acids. Remember, you can evaluate the strength of the acid by using the process of REO on the conjugate base and seeing how well that it stabilizes the negative charge. So when you have a carboxylic acid exposed to a base, the base will deprotonate that acid, grab the proton here, and that proton will leave its 2 electrons behind, leaving a carboxyl ion here. Of course, we have still the sodium positive ion. So this is referred to as a carboxylate salt, meaning that the deprotonated carboxylic acid now has a negative charge, and it is attracted to a positive charge ion, and that will make, if you remove the water, if it's dissolved in water, if you take out all the water, you'll have a solid salt here. And then the hydroxide has grabbed the proton, so it's now water. Now, in terms of evaluating the strength of this acid, we can see that there are resonance structures here with this ion. This ion is resonantly stabilized. We can, whoops, sorry, I drew the arrow the wrong way. So this negative charge here on the oxygen is actually distributed throughout the 2 oxygens. So we could draw a resonance structure like this, and that would give us R single bond O here. And then we are having a double bond to this oxygen. That's the other resonance structure here. And in terms of atom, it's on an oxygen atom. The oxygen atom stabilizes the charge moderately well, but there's also resonance, which stabilizes the charge even better. And there can be induction if there are other electron withdrawing groups attached to these carbons here, which will further increase the acidity of the conjugate acid here. So this acid is quite strong here, given that resonance stabilization of the negative ion. Now, when you name a carboxylic acid salt or a carboxylate salt, what you do is that you replace the ic acid in the name of the acid with O8 here. So, for example, this group here would be called benzoic acid. If you turn it to a carboxylic acid salt, you're deprotonating the hydrogen, and then you are then you'll have a salt containing the positive ion. If you use sodium hydroxide, let's say, to deprotonate it, you would get a sodium ion. And this is referred to as sodium benzoate, and that's a name you might have heard before because it's a very common preservative in foods. So this is a name you might have seen before. Now, in terms of the relative acidities of these carboxylic acids, generally we can say that carboxylic acids are strong enough acids that at neutral pH they will be deprotonated by water itself here to some extent. And so we can draw this arrow here. So the water is grabbing the proton here from the carboxylic acid, and the lone pair is being left behind, leaving this oxygen with 3 lone pairs and a negative and 1 bond, giving it a negative formal charge. The oxygen here also with 3 bonds and 1 lone pair, giving it a positive formal charge. It's a hydronium ion. And the pKa of most carboxylic acids is going to be somewhere between 4 and 5. So when we compare these two acids and we try to see which side of the equilibrium would be favored, when we look at the hydronium ion here, the pKa of the hydronium ion is going to be lower than that of the carboxylic acid. So this side of the equilibrium will be favored, the protonated form in an acidic environment, right? The acid will protonate the carboxylic acid. But if it's a neutral environment, you'll have a decent some kind of equilibrium here, favoring the carboxylic acid side a little bit. Now, the pKa of the most carboxylic acid is going to be somewhere between 4 and 5. So you can see that for propanoic acid here, it's 4.87. So the pKa is around 5-ish. For ethanoic acid, it's about 4.76. For butanoic acid, it's a good deal lower, and that's because when we deprotonate the acid, we're going to have even more significant resonance, right? When we deprotonate any of these, we get the resonance that we see right here with this ethanoic acid here being deprotonated. However, when we deprotonate for the benzoic acid, not only do we have resonance whoops, sorry, I needed a carbon in there. Not only do we have resonance here within our carboxylic acid group, so if this is deprotonated, we have a negative like this. We also have this benzyl situation here, so we can have this resonance structure right here, but we can also have another one where we instead, and I'm going to use a different color arrow here for this one, we have this this situation here as well, where we have a resonance throughout the ring. So that further increases the acidity, because that negative formal charge will be delocalized throughout that aromatic ring. And okay. So compared to hydrochloric acid or sulfuric acid, what we would consider strong acids, these are not particularly strong compared to them. Those are going to have pH or pKa like -7 here, -9, right, for sulfuric acid, or what's the -7? I can't remember the exact pKa's, but they're negative. Sorry, I might have gotten those wrong. But they're very strong acids. They have negative pKa's, whereas the pKa of a carboxylic acid is somewhere around 4 or 5. However, that's much lower than an alcohol, for example. An alcohol has a significantly higher pKa. It's significantly less acidic because when you deprotonate this oxygen here and make the associated negative ion, it cannot resonantly stabilize that charge in the same way as we saw with the deprotonated carboxylic acid here. That is stabilized due to that resonance. So let's think about the equilibrium between a carboxylic acid and a carboxylate salt at a physiological pH, which is around neutral. It's around 7.3. So you may recall from way back in general chemistry what was known as the Henderson-Hasselbalch Equation. And what that says is that if we have an acid that is in water and we have an equilibrium between the acid and its conjugate base, the pH of the solution with a certain concentration of acid and conjugate base is going to be the pK of the acid plus the log of the concentration of the conjugate base over the concentration of the acid. So at physiological pH, the pH is 7.3. But however, for the carboxylic acid, the pKa is around 5, right? So what we can do is we can rearrange this equation in order to solve for the ratio of the acid to the conjugate base. And so let's do that really quick. What we can do is rearrange this right here. We will rearrange this equation by subtracting the pKa from each side. Okay, and then we're going to get, and I'll continue this over here, we'll get that the log of the base, the conjugate base over the acid concentration is going to be the pH minus the pKa. Okay, and so then if we do the base 10 antilog of this involves taking the power of each side, 10 to the power of each side. That will cancel this log, and what we will get is that the concentration of the conjugate base to the acid is going to be 10 to the pH minus pKa. Okay, and so what that means is that if the pH is 7 and the pKa is, 5-ish, let's say, or 4-ish, let's say, 4 to 5, but we'll go 4. The ratio of the conjugate base to the acid concentration is going to be 10 to the 7 minus 4. That's going to be 10 to the third power. So, as we mentioned before, we're going to have a lot more of the carboxylate ion. We're going to have a deprotonated carboxylate ion as at the physiological pH and when carboxylic acids are in the body. This is going to be very important because, for example, amino acids, which make up proteins, contain the functional group amine and carboxylic acid. And so it's important to note that at physiological pHs, those carboxylic acid groups are going to be deprotonated in the body. So for the most part, in a 1,000 to 1 ratio. So you'll have 1,000 times more of the conjugate base versus the protonated acid here. So an example of that is pyruvic acid. In physiological pHs, you're not going to have pyruvic acid, probably. You're going to instead have the deprotonated pyruvate, which will be the dominant form here. And again, we'll have about 1,000 times this versus 1 times this at the physiological pH. Remember that for a carboxylic acid, where it's if we look at the deprotonated form, the conjugate base in all of these carboxylic acids is going to be stabilized by resonance. However, in terms of evaluating the strength of an acid like this, we would want to use REO on the conjugate base as described in chapter 3 on acids and bases. And so we see that the atom is oxygen, which is better than carbon for stabilizing a negative charge. The resonance here is there exists resonance, but induction, if we add induction, we can further increase the stability of the conjugate base, thus further increasing the acidity of the acid. And so if we added electron withdrawing groups like chlorines here, you can see that for the chlorinated acetic acid, having that electron withdrawing group affects the pKa by quite a lot, dropping it from 4.8 to 2.9, making the acid nearly 100 times more acidic with a chlorine group attached to the allylic to the carbon-oxygen double bond. If we add a second chlorine, this effect is enhanced further, and if we add a third, it's enhanced even further, making a quite acidic carboxylic acid with a pKa of only 0.9 here. Now, notice that if the chlorine is at the alpha carbon, the inductive effect is quite strong, and the inductive effect quickly drops off as it goes to further and further away carbons. If the electron withdrawing group is not at the alpha carbon right next to the carbonyl, but at the beta carbon, then that effect will be decreased significantly. If it's at a gamma carbon, it's almost completely gone because the pKa without any electron withdrawing group was 4.8 to begin with, and adding the chlorine at the gamma carbon only decreases it to 4.5. If you have a benzoic acid, you may have an electron, as we discussed in previous chapters here, you can have that resonance stabilization of the negative charge throughout the ring. And if you have an electron withdrawing group here, that's going to further enhance this effect. And so a strongly electron withdrawing group that we learned about in the previous chapters was a nitro group. So if that is on there, that's going to significantly decrease the pKa and make the carboxylic acid more acidic. If we have an aldehyde group here, this will have a pretty significant electron withdrawing effect. A halogen group, lesser so, but to some extent, and so forth. When we look at methyl groups, the methyl groups and the oxygen groups are not electron withdrawing, they are electron donating. So they tend to actually not affect that as much. So if we go back here, the pKa of the benzoic acid was about 4.2 by itself, right? So we can see that and that's what this one right here, a hydrogen. So if we have an electron donating group, so these are electron donating, that reduces the stabilization of the negative charge, because again, what we're doing here is with these electron withdrawing groups. So these are electron withdrawing. These are going to stabilize that negative charge by providing it another place to go, not just in the aromatic ring, but over here into the electron withdrawing group as well. Whereas if we have these electron donating groups, well, these electrons then are only stuck to the ring, and in fact there's even more electron density being donated, contributing to a greater negative charge and lower stability here. When it comes to preparing carboxylic acids, we have a number of ways that we have covered in previous chapters that allow the preparation of carboxylic acids. One way was the oxidative cleavage, using ozone followed up by a water for protonation of the products of the alkynes. So there was not a full mechanism given for this in chapter 9 regarding alkynes, but this is one way to produce carboxylic acids. What happens essentially is you split the triple bond, and on either side of the triple bond you end up with adding this group, the carboxylic acid here. So this this is the carbon here, this is this carbon, right? And then right here, this carbon here would be like this one here, for example. And what's added on is all of this right here, right? The double bond oxygen and the OH. And so if you split a triple bond, you'll get 2 carboxylic acids, with the carbon being the carbonyl carbon there, which was the carbon on the triple bond. We also talked about the oxidation of primary alcohols. If we use a powerful oxidizing agent, we will oxidize straight past the aldehyde to the carboxylic acid. So remember, if you want to oxidize and only oxidize to the aldehyde, what you would do is use PCC, and this would give us an aldehyde right here. But if we go and we use a strong oxidizing agent after that, such as sodium dichromate, in an acidic environment, then we're going to go and oxidize further. We can tell this is an oxidation looking very simply because from here to here it's an oxidation because we lose a hydrogen and we get a second bond to oxygen. So more bonds to oxygens, losing hydrogens, that's oxidation. And then here, adding an oxygen atom here between the carbon and the hydrogen to make the carboxylic acid is also adding oxygen atoms, so it's oxidation. In chapter 17, we learned about what happens when you expose a benzyl compound to strong oxidizing agent. What happens is a kind of cleavage, and so we end up at this point cleaving all the other carbons off, and we end up with a double bond to oxygen here. So this carbon here is this one here. We lose what it's attached to, but we double bond to an oxygen, and we also have an OH group here producing the carboxylic acid. And again, in this one, it's another situation where the mechanism is not completely shown. However, this is a useful synthetic reaction. Now, a reaction for which let's see, we did show here the formation of nitriles and aryl nitriles in particular in previous chapters. So these would be formed by the reaction of sodium cyanide or cyanide ions into a SN2 type reaction, as is shown similarly underneath. So I'll start with what we have on the bottom here. So we can produce a nitrile by starting with a benzene ring here, an alkyl benzene ring, halobenzyl group here, and we have an SN2-like reaction, assuming that this is not too sterically hindered, and the leaving group will simultaneously leave, and we'll end up with this nitrile. If we expose this nitrile to acid and heat, we will end up keeping this carbon. This carbon is this one right here, but ultimately we'll have a double bond to that carbon and OH, producing a carboxylic acid. So in general, taking a nitrile and exposing it to heat, we'll take this carbon and instead turn it instead of carbon triple bond nitrogen, to a carboxylic acid group here. In addition, we can do a carboxylation of Grignard reagents. So recall that Grignards are produced by taking some type of alkyl halide and reacting with magnesium, and we'll get an alkyl magnesium halide like this. And really, because the carbon is so much more electronegative than the magnesium, it's going to be taking the electrons with it, essentially. And what we get really here is we get a carbanion here, and then we have a positively formal charged magnesium, which does not involve itself in the reaction. Now, if we react this with carbon dioxide, what we're going to get is an attack by this carbanion here into this positively charged carbon. The reason why this carbon in carbon dioxide is positively charged is because it's attached to two very electronegative oxygen atoms, which pull the electron density away from this, making this carbon an electrophilic center. and so it will attract the electrons that are in the Grignard carbanion, and will have a nucleophilic attack on this carbon. Now, carbon can't have 4 bonds, or 5 bonds, so we also draw a resonance arrow here because we have a pi bond between 2 atoms of differing electronegativity, which means we can write an arrow showing those oxygen atoms or those electrons lying on the oxygen atom. At that point, we have a carboxylate anion here, and all that's left is to follow this up with acid to be protonated. So notice this oxygen now does not have a double bond to carbon. It has a single bond with not 2 lone pairs, but now 3, giving it a negative formal charge. And so if we expose it to acid, we can then protonate that carboxylic acid, and we get the ultimate carboxylic acid here. So if we're going to do a Grignard reaction to produce a carboxylic acid, what we want to do is, again, take the alkyl halide here, react with magnesium in the presence of diethyl ether here as a solvent, and we will get the alkyl magnesium bromide. And then at that point, again, we've got what's essentially a carbanion, which will attack the CO2 and produce the carboxylic acid. At that point, that's going to bring an end to this first lecture of this week. So we've covered chapters 20.1 to 20.4, where we discussed the nomenclature of carboxylic acids and some of the common carboxylic acids around. We also discussed some reactions that can be used to produce carboxylic acids, including reactions we learned in previous chapters, and also new reactions such as the hydrolysis of nitriles and the carboxylation of a Grignard with CO2. In the next lecture, we're going to discuss other reactions of carboxylic acids to produce a variety of carboxylic acid derivatives, and I look forward to seeing you in the next one. Have a good one.